Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we're going to prove that a real number is rational if and only if it has a periodic decimal expansion. So first, we're going to assume we have some periodic decimal. So we can represent any general periodic decimal as some integer part plus some non-repeating initial finite part and then the repeating part that comes after. And this we can break up. We have the integer part, the non-repeating part, let's say it goes out to L decimal units, digits. This is just b1, b2.bl. It's just b1, b2.bl over 10 to the L, which is a rational number. And then this last part, note if you have any repeating decimal, the form 0.a1a2.as. If you multiply that by 10 to the s minus 1, the a1, a2.as gets pulled to in front of the decimal. Subtracting 1 gets rid of all the repeating terms, and you're just left with a1, a2.as. So this repeating part times 10 to the s minus 1 is just one portion of the repeating part. And so this shows us that, in fact, a1, a2.as over 10 to the s minus 1 will give you the repeating decimal a1, a2.as, a1, a2, etc. And so that repeating part divided by 10 to the L, the 10 to the L takes it out to the right L units past the non-repeating part. And so our real number we see is a sum of 3 rational parts, and so it's rational. Now the other way. So we're going to assume we have some rational number. On the denominator, we can have some factors of 2 or 5. We're going to pull out any of these factors of 2 or 5. Say we have the form a over 2 to the s, 5 to the l, b, where b is relatively prime to 10. And then we're going to multiply top and bottom by 2 to the l, 5 to the s. You get 2 to the l, 5 to the s, a over 10 to the s plus l, b. And then we're going to note 10 to the phi of b is congruent to 1 mod b, because b is relatively prime to 10. This is Euler's theorem. So we can also say equivalently 10 to the phi b minus 1 is k times b. And 10 to the phi b minus 1 is just something in the form 99999, etc. So we're going to multiply the top and bottom by this integer k. And then a little bit of manipulation. We get a denominator of the form 10 to the s plus l times 10 to the phi b minus 1. That under 2 to the l, 5 to the s, ak, which is just some integer. So the first thing we're going to do via the division algorithm, we can say we can pull out some integer term and be left with a remainder that's less than the denominator. And then wherever we're left with, the remainder, we're going to again use the division algorithm to divide just by 10 to the phi b minus 1. So we're going to write that as some c times 10 to the phi b minus 1 plus d. So the c term, that's going to be our non-repeating part. We're going to pull that out. We're going to call that b1, b2.bl, where these are not being multiplied. They're just represent the digits of the non-repeating term. Solve this over 10 to the l plus l plus s. So that's a non-repeating part. The repeating part, the remainder again, it's just something in the form a1, a2.as. Again, this just represents the digits of the remainder, the s digits, and this is all divided by 10 to the l plus s, 10 to the phi b minus 1. So this will be the repeating part. And so now we wrote our general rational number in terms of, in this format. This format is just integer part, plus non-repeating part, plus repeating part, which is our general repeating decimal format. And that proves it. Thanks for watching. Please check out our blog, check out centerofmath.org, and follow us on Facebook and Twitter. Thank you.